Welcome. In this lecture, we discuss the definition of dimension of a vector space. So suppose we consider a set that is both linearly independent and spanning, and suppose that in this case we denote the elements of such set as v1, v2, v3, and then v sub t denotes the number of members of such set. So what we're saying here is that the span of this set under consideration is equal to, this is the set, and the span of this set is exactly equal to the entire vector space we're considering, because that set has that spanning property. And also this set has the linearly independent property, so members of that set are linearly independent. Then we refer to this set as a basis for this vector space V. A very important factor here is that the number of members of the number of elements of this basis is denoted by the that number is denoted here as t. So we define the dimensionality, the dimension of the vector space, as the number of members of the basis. So in this case, we would say the dimension of such vector space is exactly equal to the number of elements of the basis for the vector space. And so there are some examples. We would say that the dimension of CM, the vector space of column vectors with m entries, the dimension of that vector space is m. So in other words, if we want to have an example of this, the dimension of C4 would be 4. So, excuse me, we know that one such basis of C4 is the set that contains E1, E2, E3, and E4. These are called the standard unit vectors. And any member of C4 can be expressed as a linear combination of each of these vectors is one column of the identity matrix, right? So we have a refresher here. This is what E1 looks like, and E2 is going to have 1 in position 2, E3 will have 1 position 3, E4 will have 1 position 4, and zeros everywhere else. Any member of C4 can be expressed as a linear combination of these standard unit vector. The vector space of matrices with m rows and n columns has dimension mn. So here's another illustration of this. Let's say the dimension of the vector space m22 or m sub 2, this vector space has dimension 4. The dimension of the vector space m53, for example, this would be a vector space with dimension 15, and so on, right? So is that product of the number of rows multiplied by the number of columns of the matrix, of the matrices, is precisely what is defined as the dimension of this vector space. Central to the study of linear algebra is the definition of nullity and rank. And we are going to define the nullity in terms of the dimension of the null space of a matrix. So, and there will be, you will see, this is basically a way of dubbing or finally establishing a formal name for something that we have learned for quite a while now, how to calculate and how to compute. You will see the calculation of this number, of this dimension of the null space, is something that we're quite familiar with, because it is a calculation that relies on RREF. But in short, the nullity is going to be the dimension of the null space of the matrix, and the other dimension that it's significant here is the dimension. This is the dimension of the column space of the matrix. So in our RREF calculation, we are always we're used to determine the number of leading ones, the number of pivot columns with the letter R. And for a matrix that has n columns, we would say that n minus R, n being the number of columns of the matrix and R being the number of leading ones, n minus R is well, so far we had known both of these quantities, R as being the number of elements in the set D, and n minus R the number of elements in the set F. But now we're going to give this a name. So little r stands for rank, and rank is another form of calling the dimension or the dimensionality of the column space. And n minus r will be considered the dimensionality or dimension of the null space, also called the nullity. So let's illustrate both of these definitions, the definition of rank and the definition of nullity. Let's remember, rank is the dimension of the column space. It also is the dimension, it's also the number of leading ones in the RREF, and n minus r will be the dimension of null space, also known as nullity. So here we have a matrix. This matrix has let's see, 2, 4, 6, 7 columns. Okay, so this matrix has 2, 4, 6. This matrix is 6 by 7. It has 2, 4, 6 rows and 7 columns. So in this case, we would say that n equals 7. The number of columns of this matrix is 7. And if we calculate the RREF of this matrix, then we find that this matrix row reduces to this, is row equivalent to this RREF matrix, which has 1, 2, 3, 4. In this case, we would say that R equals 4. So this is exactly the dimension of the column space of this matrix, and that's also called the rank. And in this case, n minus r would be 7 minus 4, which is the dimension of the null space of the matrix. So in this case, we would say that the rank of the matrix is 4. So this is what we call the rank. And we would say that the nullity of this matrix, the nullity here is 3. So it has rank 4 and nullity equals to 3. So a little more detail here. The indices that store in set D are 1, 3, 4, and 6. And the indices on set F are 2, 5, and 7. And as we have established, the rank, in this case, the dimension of the column space is 4, and the dimension of the null space is 3. And so one thing we remember from that theorem basis of a null space is that we could, by reading this RREF, we could come up with 3 vectors. This is because precisely n minus r, the nullity, equals 3. And these 3 vectors are going to have 1s and 0s on positions 2. Here we're going to put a 1 here, and then position 5, let's see, 1, 2, 3, 4, position 5, and position 7 in this vector are going to be 0, and then position 2 is going to be 0, and in position 1 we're going to have a 1, excuse me, in position 5 we're going to have a 1, and then position in position 7 we're going to have a 0, and in the last vector we're going to have 0 in position 2, 0 in position 5, and 1 in position 7. So we can place 1s and 0s on positions determined by the indices in the set F, and then the other entries are filled with the negative of entries on columns 2, 5, and 7. So this set here, this is a set with 3 vectors. This set is precisely what's considered a basis for the null space, and because this basis has 3 elements, then that is the underlying reason why the dimension of the null space in this case is equal to 3. And this theorem is putting in perspective, is bringing together the information on dimensionality of the column space and dimensionality of the null space. And one thing that is implied here is that if we add the rank and the nullity of the matrix, this excuse me, this would be adding R plus n minus R, then we see that this equals the number of columns in the matrix. So the dimension of the column space added to the dimension of the null space is always going to add to the number of columns in the matrix. And this is a theorem that is known as the fundamental theorem of linear algebra. If we consider this matrix that has 1 row and 3 columns, it's quite straightforward to calculate the RREF of this matrix because the RREF of this matrix is basically something that requires 1 step, or you can argue it requires 0 steps. So the number of pivot columns, the number of leading ones in this case is 1, which means the rank of this matrix is 1, and the nullity is given by the number of columns minus the rank. So in this case the nullity is 2. So it's also quite straightforward to see that the null space of this matrix is the set of excuse me, is the set of vectors in C3 for which this equation is satisfied. The number of solutions of this homogeneous system, and the null space has dimension 2.